Hi, my name is Mr. Evangelista, and welcome to another episode of Evangelista Science. In this episode, we're going to be talking about 1-2 of the IB Chem SL curriculum, which is the mole concept. You can just see here some of the objectives and some of the concepts that we're going to be talking about. So let's get started. What is the mole? The mole is just a number, just like how a dozen is equal to 12, 4 score and 7 years ago, so score is equal to 20. The mole is also just a number. It's a rather large number. It's 6.02 times 10 to the 23. So it's a really large number, and we call this number Avogadro's number. Now I looked up, how would you say 6.02 times 10 to the 23? I think it's 600 sextillion. So that, just to put this in perspective, if you were to give out 600 sextillion pennies to everyone on Earth, everyone would be a trillionaire. So it's a large amount of you know. And why would we need this number in chemistry? Well, let's say I told you to go weigh out one atom of something. Well, that would be really difficult. You put one tiny little grain of a compound on the scale, and you already have hundreds and thousands of atoms there. How the heck are you going to get just one atom? And so we use the mole because atoms and molecules are so tiny. We use the mole to kind of amplify the quantities that we're working with so that they're easier to work with, and we're not trying to just take out just one atom. We're actually dealing with a lot of atoms because we're multiplying it by such a large number. So let's take a look here. Here we have several different compounds, and we have Avogadro's number of molecules of each of these compounds. So I have 600 sextillion molecules of potassium iodide here. I have 600 sextillion molecules of cobalt nitrate here. Notice they all weigh differently because they're all made of different elements in different ratios, but we still have 1 mole or 600 sextillion molecules of each, and here they're shown with their different weights. How do we calculate this weight? Let's take a look at 1 molecule of chlorine gas. So chlorine is Cl2. How could you figure out the formula of chlorine? Well, chlorine is one of the diatomics because it's a Brinkelhoff element. Brinkelhoff is bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, fluorine. Brinkelhoff. Any one of those elements is diatomic, meaning it's going to come in a pair. It's going to come in twos. And so I look at the periodic table and I can find the molar mass of 1 mole of chlorine. So 1 mole of chlorine or 600 sextillion molecules of chlorine would weigh 35.45 grams. Now I have 2 of those. If I multiply it by 2, I get the molar mass of chlorine, or how much 1 mole of a molecule of chlorine, 1 mole of molecules of chlorine would weigh 70.90 grams. Let's take a look at ammonium nitrate. So nitrogen's 14, hydrogen's 1, oxygen's 16. I have 2 nitrogens, 4 hydrogens, and 3 oxygens. I know that's cut off a little bit there, but it comes out to 80.06 grams when you add it all up. Here we have aluminum sulfate. Aluminum is about 27, sulfur is about 32, and we said oxygen 16. So sulfate itself comes out to 96.07 grams. But if we look, we have 3 of those. So together, 3 sulfate molecules come out to 288.21. Add that with 2 aluminum, and the molar mass, we get 342. So how do we go from grams to moles or moles to grams? Well, if we're going from grams to moles, we're going to divide by the molar mass. And if we're going from moles to grams, we're going to multiply by the molar mass. And again, I find the molar mass in the periodic table. Let's do some problems. So 10 moles of chlorine, and I want to convert this to grams. Well, if I'm going from moles to grams, I'm going to multiply by the molar mass. We found the molar mass earlier to be about 70, so 10 times 7.9 would give you 709. What if I want to go the other way? Well, if I want to go from grams to moles, again, I now divide by the molar mass. Again, you find the molar mass in the periodic table. So 10 divided by 70.9 is 0.14 moles of chlorine. Let's talk about particles. I can have several different particles. So I can have molecules like oxygen, Brinkelhoff element. I can have atoms, or I can have formula units like this ionic compound salt, sodium chloride. And if I wanted to go from particles to moles, I'm going to divide by Avogadro's number. If I want to go from moles to particles, I'm going to multiply by Avogadro's number. So if I had 10 moles of chlorine, how many molecules would that be? So to go from moles to molecules, I'm going to multiply by Avogadro's number. So 10 times 6.02 times 10 to the 23, I get 6.02 times 10 to the 24 molecules. Now, what if I wanted to find out atoms? Well, we know that 10 moles is equal to 6.02 times 10 to the 24 molecules. And we can see that each molecule of chlorine has 2 atoms of chlorine. So if we just multiply this number by 2, we can actually get the number of atoms of chlorine. Empirical formulas and molecular formulas. Empirical formulas are the simplest whole number ratio of elements. So let's take a look here. Here we can see the simplest ratio is CH2. That is the simplest whole number ratio possible. We can have different molecular formulas that come from the same empirical formula. So here this is ethene. We have a carbon double bonded to a carbon, so we have C2H4. And here we have C3H6, but both of them have the base formula of CH2, or the empirical formula. The molecular formula, which is these right here, show the actual atoms present in the molecule. And it's going to be a multiple of the empirical formula. So let's do some problems. What is the percentage of sulfur in sulfur dioxide? So sulfur is 32 grams, sulfur dioxide is 64 grams. Again, I can find those in the periodic table. To find out the percentage of sulfur, I would just set up a ratio, and I get about 50%. Let's do some empirical formula problems. Now, the trick with these is to assume, if they give you percentages, is to assume you have 100 grams. So if I had 100 grams, then I would have 38.67 grams, I would have 16.22 grams, and I would have 45.11 grams of nitrogen. If I divide those by their molar masses, which I find in the periodic table, I can get the moles. So I have 3 moles of carbon, 16 moles of hydrogen, and 3 moles of nitrogen. I'm going to figure out the ratio. So the ratio is about 1 to 5 to 1. And from there, I can figure out that the empirical formula is CH5N. Let's do another one. Caffeine now has to do with molecular formulas. Caffeine has a molar mass of 194, and its empirical formula is C4H5N2O. What is its molecular formula? And so let's find the molar mass. Again, I find that in the periodic table of the empirical formula. They told me that the molar mass of the substance was 194 grams. So if the molecular formula is just a multiple of the empirical formula, we need to figure out what that multiple is. We can set up this ratio here, and we can figure out that the multiple is 2. And so all we'd have to do is multiply the empirical formula by 2 to get our molecular formula. So the molecular formula is C8H10N4O2.